What time is it at your side of the world? Let us compare Standard Time and Universal Time. Welcome back to our channel. Standard Time is the synchronization of clocks within a geographical region to a single time standard, rather than a local mean time standard. Generally, Standard Time agrees with the local mean time at some meridian that passes through the region, often near the center of the region. Historically, Standard Time was established during the 19th century to aid weather forecasting and train travel. Applied globally in the 20th century, the geographical regions became time zones. The standard time in each time zone has come to be defined as an offset from universal time. A further offset is applied for part of the year in regions with daylight saving time. The adoption of standard time, because of the inseparable correspondence between time and longitude, solidified the concept of having the globe into an eastern and western hemisphere, with one prime meridian replacing the various prime meridians that had previously been used. During the 19th century, scheduled steamships and trains required time standardization in the industrialized world. Great Britain. A standardized time system was first used by British Railways on December 1, 1847, when they switched from local mean time, which varied from place, to Greenwich Mean Time, GMT. It was also given the name railway time, reflecting the important role the railway companies played in bringing it about. The vast majority of Great Britain's public clocks were standardized to GMT by 1855. North America. Until 1883, each United States railroad chose its own time standards. The Pennsylvania Railroad used the Allegheny time system, an astronomical timekeeping service which had been developed by Samuel Pierpont Langley at the University of Pittsburgh's Allegheny Observatory, then known as the Western University of Pennsylvania, located in Pittsburgh, Pennsylvania. Instituted in 1869, the Allegheny Observatory's service is believed to have been the first regular and systematic system of time distribution to railroads and cities, as well as the origin of the modern standard time system. By 1870, the Allegheny time service extended over 2,500 miles with 300 telegraph offices receiving time signals. However, almost all railroads out of New York ran on New York time, and railroads west from Chicago mostly used Chicago time, but between Chicago and Pittsburgh/Buffalo the norm was Columbus time, even on railroads such as the PFTWNC and LS and MS, which did not run through Columbus. The Santa Fe Railroad used Jefferson City, Missouri, time all the way to its west end at Deming, New Mexico, as did the east-west lines across Texas. Central Pacific and Southern Pacific Railroads used San Francisco time all the way to El Paso. The Northern Pacific Railroad had 7 time zones between St. Paul and the 1883 west end of the railroad at Wallula, JCT. The Union Pacific Railway was at the other extreme, with only 2 time zones between Omaha and Ogden. In 1870, Charles F. Dowd proposed 4 time zones based on the meridian through Washington, D.C. for North American railroads. In 1872 he revised his proposal to base it on the Greenwich Meridian. Sandford Fleming, a Scottish-born Canadian engineer, proposed worldwide standard time at a meeting of the Royal Canadian Institute on February 8, 1879. Cleveland Abbey advocated standard time to better coordinate international weather observations and resultant weather forecasts, which had been coordinated using local solar time. In 1879 he recommended 4 time zones across the contiguous United States, based upon Greenwich Mean Time. The General Time Convention, renamed the American Railway Association in 1891, an organization of U.S. railroads charged with coordinating schedules and operating standards, became increasingly concerned that if the U.S. government adopted a standard time scheme it would be disadvantageous to its member railroads. William F. Allen, the convention's secretary, argued that North American railroads should adopt a 5-zone standard, similar to the one in use today, to avoid government action. On October 11, 1883, the heads of the major railroads met in Chicago at the Grand Pacific Hotel and agreed to adopt Allen's proposed system. The members agreed that on Sunday, November 18, 1883, all United States and Canadian railroads would readjust their clocks and watches to reflect the new 5-zone system on a telegraph signal from the Allegheny Observatory in Pittsburgh at exactly noon on the 90th meridian. Although most railroads adopted the new system as scheduled, some did so early on October 7 and others late on December 2. The Intercolonial Railway serving the Canadian Maritime provinces of New Brunswick and Nova Scotia just east of Maine decided not to adopt intercolonial time based on the 60th meridian west of Greenwich, instead adopting Eastern Time, so only 4 time zones were actually adopted by U.S./Canadian railroads in 1883. Major American observatories, including the Allegheny Observatory, the United States Naval Observatory, the Harvard College Observatory, and the Yale University Observatory, agreed to provide telegraphic time signals at noon Eastern Time. Standard Time was not enacted into U.S. law until the 1918 Standard Time Act established Standard Time in time zones. The law also instituted Daylight Saving Time, DST. The Daylight Saving Time portion of the law was repealed in 1919 over a presidential veto, but was re-established nationally during World War II. In 2007 the U.S. enacted a federal law formalizing the use of Coordinated Universal Time as the basis of Standard Time, and the role of the Secretary of Commerce, effectively, the National Institute of Standards and Technology, and the Secretary of the Navy, effectively, the U.S. Naval Observatory, in interpreting Standard Time. In 1999, Standard Time was inducted into the North America Railway Hall of Fame in the category National, Technical Innovations. The Dominion of Newfoundland, whose capital St. John's falls almost exactly midway between the meridians anchoring the Atlantic Time Zone and the Greenland Time Zone, voted to create a half-hour offset time zone known as the Newfoundland Time Zone, at 3.5 hours behind Greenwich time. The Netherlands. In the Netherlands, introduction of the railways made it desirable to create a standard time. On May 1, 1909, Amsterdam time or Dutch time was introduced. Before that, time was measured in different cities. In the east of the country, this was a few minutes earlier than in the west. After that, all parts of the country had the same local time, that of the Wester Tower in Amsterdam, Westertoren/4°5301.95 E. This time was indicated as GMT plus 0H19M32.13s until March 17, 1937, after which it was simplified to GMT plus 0H20M. This time zone was also known as the Loenen time or Gorinchem time, as this was the exact time in both Loenen and Gorinchem. At noon in Amsterdam, it was 11:40 in London and 12:40 in Berlin. The shift to the current Central European time zone took place on May 16, 1940. The German occupiers ordered the clock to be moved an hour and 40 minutes forward. This time was kept in summer and winter throughout 1941 and 1942. It was only in November 1942 that a different winter time was introduced, and the time was adjusted 1 hour backwards. This lasted for only 3 years. After the liberation of the Netherlands in 1945, summer time was abolished for over 30 years, so during those years, Standard Time was 40 minutes ahead of the original Amsterdam time. As of 2017, the Netherlands is in line with Central European Time, GMT plus 1 in the winter, GMT plus 2 in the summer, which is significantly different from Amsterdam time. New Zealand. In 1868, New Zealand was the first country in the world to establish a nationwide standard time. A telegraph cable between New Zealand's 2 main islands became the instigating factor for the establishment of New Zealand time. In 1868, the Telegraph Department adopted Wellington time as the standard time across all their offices so that opening and closing times could be synchronized. The Post Office, which usually shared the same building, followed suit. However, protests that time was being dictated by one government department, led to a resolution in Parliament to establish a standard time for the whole country. The director of the Geological Survey, James Hector, selected New Zealand time to be at the meridian 172 degrees 30 minutes east. This was very close to the country's mean longitude and exactly 11 plus 12 hours in advance of Greenwich Mean Time. It came into effect on November 2, 1868. For over 50 years, the Colonial Time Service Observatory in Wellington determined the correct time each morning. At 9 a.m. each day, it was transmitted by Morse code to post offices and railway stations around the country. In 1920, radio time signals began broadcasting, greatly increasing the accuracy of the time nationwide. Universal Time, UT or UT1, is a time standard based on Earth's rotation. While originally it was mean solar time at 0 degrees longitude, precise measurements of the Sun are difficult. Therefore, UT1 is computed from a measure of the Earth's angle with respect to the International Celestial Reference Frame, ICRF, called the Earth Rotation Angle, ERA, which serves as a modern replacement for Greenwich Mean Side Real Time. UT1 is the same everywhere on Earth. Prior to the introduction of Standard Time, each municipality throughout the clock-using world set its official clock, if it had one, according to the local position of the Sun, see Solar Time. This served adequately until the introduction of rail travel in Britain, which made it possible to travel fast enough over long distances to require continuous resetting of timepieces as a train progressed in its daily run through several towns. Starting in 1847, Britain established Greenwich Mean Time, the mean solar time on the prime meridian at Greenwich, England. To solve this problem, all clocks in Britain were set to this time regardless of local solar noon. Using telescopes, GMT was calibrated to the mean solar time at the Royal Observatory, Greenwich in the UK. Chronometers or telegraphy were used to synchronize these clocks. As international commerce increased, the need for an international standard of time measurement emerged. Several authors proposed a universal or cosmic time, see time zone worldwide time zones. The development of universal time began at the International Meridian Conference. At the end of this conference, on October 22, 1884, the recommended base reference for world time, the Universal Day, was announced to be the local mean solar time at the Royal Observatory in Greenwich, counted from 0 hours at Greenwich Mean Midnight. This agreed with the civil Greenwich Mean Time used on the island of Great Britain since 1847. In contrast, astronomical GMT began at mean noon, i.e. astronomical day X began at noon of civil day X. The purpose of this was to keep one night's observations under one date. The civil system was adopted as of 0 hours, civil, January 1, 1925. Nautical GMT began 24 hours before astronomical GMT, at least until 1805 in the Royal Navy, but persisted much later elsewhere because it was mentioned at the 1884 conference. Greenwich was chosen because by 1884 2/3 of all nautical charts and maps already used it as their prime meridian. During the period between 1848 and 1972, all of the major countries adopted time zones based on the Greenwich Meridian. In 1928, the term Universal Time, UT, was introduced by the International Astronomical Union to refer to GMT, with the day starting at midnight. The term was recommended as a more precise term than Greenwich Mean Time, because GMT could refer to either an astronomical day starting at noon or a civil day starting at midnight. As the general public had always begun the day at midnight, the timescale continued to be presented to them as Greenwich Mean Time. When introduced, broadcast time signals were based on UT, and hence on the rotation of the Earth. In 1955 the BIH adopted a proposal by William Markowitz, effective January 1, 1956, dividing UT into UT0, UT as formerly computed, UT1, UT0 corrected for polar motion, and UT2, UT0 corrected for polar motion and seasonal variation. UT1 was the version sufficient for many astronomical and geodetic applications, while UT2 was to be broadcast over radio to the public. UT0 and UT2 soon became irrelevant due to the introduction of Coordinated Universal Time, UTC. Starting in 1956, WWV broadcast an atomic clock signal stepped by 20 milliseconds increments to bring it into agreement with UT1. The up to 20 milliseconds error from UT1 is on the same order of magnitude as the differences between UT0, UT1, and UT2. By 1960, the US Naval Observatory, the Royal Greenwich Observatory, and the UK National Physical Laboratory had developed UTC, with a similar stepping approach. The 1960 URSI meeting recommended that all time services should follow the lead of the UK and US and broadcast coordinated time using a frequency offset from cesium aimed to match the predicted progression of UT2 with occasional steps as needed. Starting January 1, 1972, UTC was defined to follow UT1 within 0.9 seconds rather than UT2, marking the decline of UT2. Modern civil time generally follows UTC. In some countries, the term Greenwich Mean Time persists in common usage to this day in reference to UT1, in civil timekeeping as well as in astronomical almanacs and other references. Whenever a level of accuracy better than 1 second is not required, UTC can be used as an approximation of UT1. The difference between UT1 and UTC is known as DUT1. Apart from Nepal Standard Time, UTC plus 5:45, the Chatham Standard Time Zone, UTC plus 12:45, used in New Zealand's Chatham Islands and the officially unsanctioned Central Western Time Zone, UTC plus 8:45, used in Eucla, Western Australia and surrounding areas. All time zones in use are defined by an offset from UTC that is a multiple of half an hour, and in most cases a multiple of an hour. Historically, universal time was computed from observing the position of the sun in the sky. But astronomers found that it was more accurate to measure the rotation of the Earth by observing stars as they crossed the meridian each day. Nowadays, UT in relation to International Atomic Time, TI, is determined by very long baseline interferometry, VLBI, observations of the positions of distant celestial objects, stars and quasars, a method which can determine UT1 to within 15 microseconds or better. Additional data sources include laser ranging of the Moon and artificial satellites, as well as the determination of GPS satellite orbits. The rotation of the Earth and UT are monitored by the International Earth Rotation and Reference System Service, IERS. The International Astronomical Union also is involved in setting standards, but the final arbiter of broadcast standards is the International Telecommunication Union or ITU. The rotation of the Earth is somewhat irregular and also is very gradually slowing due to tidal acceleration. Furthermore, the length of the second was determined from observations of the Moon between 1750 and 1890. All of these factors cause the modern mean solar day, on the average, to be slightly longer than the nominal 86,400 SI seconds, the traditional number of seconds per day. As UT is thus slightly irregular in its rate, astronomers introduced ephemeris time, which has since been replaced by terrestrial time, TT. Because universal time is determined by the Earth's rotation, which drifts away from more precise atomic frequency standards, an adjustment, called a leap second, to this atomic time is needed since, as of 2019, broadcast time remains broadly synchronized with solar time. Thus, the civil broadcast standard for time and frequency usually follows international atomic time closely, but occasionally step, or leap, in order to prevent them from drifting too far from mean solar time. Barycentric dynamical time, TDB, a form of atomic time, is now used in the construction of the ephemerides of the planets and other solar system objects, for two main reasons. 21st, these ephemerides are tied to optical and radar observations of planetary motion, and the TDB time scale is fitted so that Newton's laws of motion, with corrections for general relativity, are followed. Next, the time scales based on Earth's rotation are not uniform and therefore, are not suitable for predicting the motion of bodies in our solar system. Thank you for watching the entire video. Stay with us by subscribing.